So we have the great fortune of having Professor Diptiman Sen of the Indian Institute of Science, Bangalore, talk about uh, in the first lecture introducing quantum mechanics, so that you can follow his later lecture, which will be on quantum games. So, you have been looking at classical games, but it turns out that there's also a quantum version of that which is possible. And those of you who are particularly coming from physics might be very interested to see how you can take the classical games into a quantum realm and what kind of new features emerge. And Professor Shane is the right person to talk about it because he's been working on this for a fairly long time. I mean, at least a decade. And he's also a fantastic teacher, and I've had the fortune of listening to several of his lectures while I was a postdoc at IISc. So Professor Shane was with the Center for Theoretical Studies, and he's currently still with the Department of Physics. So without further ado, let me ask Professor Shane to give his lecture, the first of which will introduce quantum mechanics for those of you who are not familiar with it, and give you some introduction to two-state systems and entanglement, which will be useful for the second talk on quantum games. So Professor Shane, can I please invite you to give the talk?
So thank you, Sita bro, for this very kind introduction, and also for inviting me to give these talks. I realize that quantum games may be a little out of place in this meeting, but let's see. At least I find it interesting, and I hope you'll also find it interesting. Um, but I thought I would give a first talk to just introduce you to the basics of quantum mechanics, only the parts of only the aspects of quantum mechanics that will be needed in the second talk on quantum games. So this may be familiar. What I'm going to say about quantum mechanics may be familiar to many of you, but let me tell you what we need for the second talk. And please feel free to interrupt. I guess you can always do that, right? Um, so you can always ask a question at any point. Okay, so this is a talk on the basics of quantum mechanics, particularly two-state systems and entanglement. Okay, and here's my email address. So if you have any questions, you can ask me later also by sending me an email. Okay, so the outline of the talk is as follows. So first, I'll tell you a very, very basic, maybe 2-slide or 3-slide introduction to quantum mechanics. Then I'll tell you about two-state systems, which are also called qubits. Then the idea of entanglement, particularly the simplest context being the entanglement between two qubits. And finally, I'll tell you about the Bell inequality. So let me just ask, is everything I'm saying clearly audible?
Yes.
Okay, great. Yeah. Okay, so here are some basics of quantum mechanics. So first of all, a particle can be in one of many states, and each state is described by a wave function or an amplitude, psi. Now, in general, this psi can be a function of both space and time. Space, depending on how many dimensions there are, x or x, y, z. And the wave functions are complex numbers whose magnitude squared, that is mod psi squared, gives the probability or probability density of finding the particle at that space-time point. Now, whether it describes a probability or a probability density depends on the situation. So it goes like this. So if the states form a continuous set, like the position x of a particle moving in one dimension, then mod psi squared describes the probability density. What that means is that if you consider a small region from in space, small region going from x to x plus dx, then mod psi squared dx is the probability of finding the particle in that region at a time t. So this psi can also evolve in time in a way that I'll briefly describe later. Now, since the total probability of finding the particle somewhere in space must be 1, we have the normalization condition, the integral of dx over the entire range of x of mod psi squared should be equal to 1. Okay, so this is the case where mod psi squared gives you the probability density. On the other hand, if the states form a discrete set, like a particle in a finite sized box, or in a simple harmonic potential, or in the hydrogen atom, or the spin states of a particle, which I'll talk about in detail later. In these cases, mod psi squared is the probability of finding the particle in state J. So every state J will have an associated wave function psi j, and then mod psi j squared will be the probability of finding the particle in that state. Now, another feature of quantum mechanics is that it's a linear theory in terms of the wave function psi, and you can superpose wave functions. So if you have several wave functions psi 1, psi 2, psi 3, etc., which are all solutions of some equation which I'm going to come to, you can superpose them, and that will also be an allowed wave function. So in general, you can add up many wave functions, or you can integrate over many functions, depending on whether the states form a discrete set or a continuous set. You can add up wave functions before you calculate the mod psi squared. Now, here's a very important feature of quantum mechanics. It's a probabilistic theory, unlike classical mechanics, where one can in principle measure any property, like the position and momentum of any particle with infinite accuracy. And every time you make the measurement for the same configuration of particles and positions, you would always get the same values of position and momentum. Okay, so it's a completely deterministic theory, classical mechanics. Quantum mechanics is not like that. Quantum mechanics is a probabilistic theory. So given a state, we only know the probabilities of getting different values of an observable. Observable means position or momentum, for example. And every time we measure the value of an observable, so let's consider an observable which I'll call R, capital R. Every time you measure the value of this, you may get a different value. So let me call it Rj, small rj, where a j is the result of measurement number j. So you can make, say, million measurements, so j will go from 1 to 1 million. So if you make the measurement a very large number of times, you find that the values Rg are found with a probability Pj. And this is what you get experimentally, but you can also predict this if you know the wave function. So Pj will be given by the probability or probability density that you get from the wave function psi. Okay, so you have all these series of measurements, you get various values Rj with some probability Pj. Then the expectation value of the observable is denoted by this quantity. I've written it in a particular form, which is the form that is used in quantum mechanics. This is called the bracket notation. So you have a psi on the left called the bra, and then the observable R in the middle, and the psi on the right called the ket. So this is just a symbol. What it really means is the expectation value of R. So E stands for expectation value, is equal to the sum over all the different values that you can get, Rj, multiplied by the probability Pj of getting that particular value. Okay. Okay, the next feature of quantum mechanics that we really need to know for the talk on quantum games is that there are two state systems. For instance, an electron has a spin angular momentum, and the value of the spin angular momentum of the electron is fixed, is equal to half of what's called the Planck's constant, so h bar over 2, and h bar over 2 has these dimensions of energy times time. Okay, so the value of h bar over 2 is something 0.527 into 10 to the minus 34. It's actually known very, very accurately. I'm only showing you three significant figures here. Okay, so the value of so this is the magnitude of the total spin. Now you can measure the value of the spin in any direction you like, and you find that the value of the component of the spin in any direction is quantized. Okay, and it can only take the values plus h bar by 2 or minus h bar by 2. It can't take the values, for example, h bar by 3 or 3/4 h bar. So this is very peculiar, and it's a really quantum feature. This is completely different from classical mechanics, where if you consider a rotating object, like a rotating top, say you start rotating it somehow, and then you measure its component in any direction you like, and you'll find that it can take a continuous range of values, right? If you measure its component of its angular momentum in the x direction or y direction or z direction or some other direction, you'll find that it can take different values, and it keeps changing with time. The rotating top, as you know, it precesses or it slows down, and when it does any of those things, the value of its component in the spin in any direction will keep changing with time. Okay, so spin is a really purely quantum property of an electron, and it has no classical counterpart. It never changes with time. Okay, so there's no question of the spin of an electron slowing down, for example. Also, as far as we know, uh, till today, all experiments have shown that an electron is a point particle. It has no substructure. This is very different, for example, from a hydrogen atom, which has inside it an electron and a proton. An electron by itself has no smaller substructure. And if the electron was really a classical particle, you would not be able to explain why it has spin, because a point particle, um, it has no spatial extent, and therefore you can't really think of it as rotating about anything, about its own center of mass. So a classical point particle cannot have spin angular momentum. So the fact that the electron has a spin angular momentum tells you that it's a quantum property. So we call an electron a spin half particle, and the spin part has two possible states. As I said, in any direction it can be either plus h bar by 2 or minus h bar by 2. So actually there are many particles in nature which have spin half. So electron is one of them. Then there's the proton also has spin half, so does the neutron or neutrino and so on. But the electron is probably the easiest and most studied elementary particle. And so I'm just going to talk about the electron here. But you can have atoms which have spin half and so on. It turns out that there are also quanta of electromagnetic radiation, which you're familiar with. They're called photons. Electromagnetic radiation actually has a very wide spectrum. Only the observable or visible light is only a small part of the spectrum. You can have infrared, ultraviolet, X-rays, radio waves. And quanta of any of these kinds of radiation are called photons. They have spin 1. Now, this is in contrast to the electron, which has spin half. So what does spin 1 mean? It means that if you take a photon and you measure the component of its spin along the direction of its motion, you find that it can only be plus h bar or minus h bar. In terms of, so this is the quantum property again, that the spin of a photon is quantized in these two values. If you go back to a classical picture of electromagnetic radiation, we know that classically there are two possibilities for an electromagnetic wave propagating in space, which is that it can either be left circularly polarized or right circularly polarized. Okay, so it turns out that when you go from classical electromagnetism to quantum electromagnetism, left circularly polarized electromagnetic wave corresponds to a photon with spin angular momentum plus h bar, and right circularly polarized corresponds to minus h bar. So once again, you find that the polarization has two possible states. By the way, there's something slightly odd here. Normally, a spin 1 particle in quantum mechanics has 3 spin states, plus h bar, 0, or minus h bar. But a photon is a little special, and turns out it's a long story. But basically, because a photon is massless, it has only two possible states, plus h bar or minus h bar. Okay, so in that sense, it's kind of similar to an electron, which also has two possible spin states. Okay, so the next thing we need to know, well, actually, we don't really need this for the quantum games talk, but just to complete the story about basic quantum mechanics, it turns out that the wave function psi of a particle or a system of particles, it can change in time. And its time evolution is governed by a first order differential equation called the Schrodinger equation. And it has this form, I times the Planck's constant times del by del t of psi is equal to something called the Hamiltonian acting on the wave function psi. Now, the form of the Hamiltonian depends on, again, on the kind of system and wave function that you're talking about. So if you have a particle with a continuous set of states, such as states which are labeled, so let's say one particle moving in one dimension, states are labeled by the position of the particle x, then it turns out H is generally a differential operator, second order differential operator, such as the one written here, is minus h bar squared by twice m times second derivative, del squared by del x squared, where m is the mass of the particle. On the other hand, if a particle has only a discrete set of states, like a spin, if you look at the spin half, so it has only two states, 1 and 2, then the wave function is a column with two entries. So let me call it alpha and beta. So alpha is the upper entry and beta is the lower entry of the column. What does this mean? So what this psi equal to alpha beta means is that the alpha and beta are complex numbers which denote the amplitudes for the particle to be in the states 1 and 2 respectively. Okay, so alpha is the amplitude to be in state 1, beta is the amplitude to be in state 2. And of course, since the total probability is 1, we must have mod alpha squared plus mod beta squared is equal to 1. So if you look at this such an Hamiltonian, which is a 2 by 2 Hermitian matrix, so Hamiltonian is almost always Hermitian, so that the eigenvalues are real. The eigenvalues of the Hamiltonian corresponding to the allowed energies of the particle. So in this case, there are only two allowed energies, epsilon 1 and epsilon 2. You can solve the Schrodinger equation. So if the way you solve a differential, this is a linear differential equation. The way you solve it is that you look at the eigenvectors of H with certain eigenvalues. So let's say psi j is an eigenvector and Ej is the corresponding eigenvalue. Then a particular solution of the Schrodinger equation is like this. Psi j as a function of time is this factor e to the power minus I Ej t by h bar times psi j. Okay, so a single eigenstate with a particular energy evolves in a very simple way with time. Now, this is a particular solution. So the general solution of the Schrodinger equation will be given by this superposition. Psi of t will be sum over all possible values of j, e to the minus I e j t by h bar times psi j, times some arbitrary complex number, cj. And we can determine these complex numbers if you know what the initial wave function at time t equals 0 is. Okay, so now I have told you that an electron can actually have two kinds of states. One is continuous, like the coordinate x, and the other is discrete, like the spin half. So what is the general story? So the general story is that you can combine these two, the continuous label x and the discrete label spin. And we write the wave function for an electron as, again, a column with two entries, alpha and beta. But this time the entries alpha, beta are functions of x and t also. So what is the interpretation now? So mod alpha squared is the probability density, right? Not the probability, probability density to find the electron at x with the component of its spin along the z direction equal to plus h bar by 2. And mod beta squared is the probability density to find the electron at x with the component of its spin along z to be minus h bar by 2. Now, of course, the choice of the z direction is arbitrary. We could have chosen some other direction to define the spin, but it's we have to follow some convention for consistency. So I've just followed the convention that the upper and lower components correspond to spin along the plus z direction and minus z direction. Okay. And the normalization now, because you have both a continuous label x and a discrete label up and down for the spin, the normalization condition integral is integral dx or mod alpha squared plus mod beta squared is equal to 1. So this tells you total probability of finding the electron somewhere in space and with some spin plus or minus h bar by 2 is equal to 1. Okay, so now in the rest of this talk and also in quantum games, we will ignore the motion of the electron in space and only look at and also ignore its time evolution. That's not important for us. We really want to concentrate on the structure of this column, alpha, beta. Okay, so we're just going to look at the spin wave function of the electron. And as I've already said, so this is a repetition. Psi is just a two-component object. Alpha and beta are the amplitudes to find the electron with the component of its spin in the z direction equal to plus or minus h bar by 2. And as I've also said earlier, you can think of this as superposition alpha times 1, 0 plus beta times 0, 1. Okay, maybe I should just pause a bit. Are there any questions so far? Okay, doesn't sound like this. So if there are no questions at this point, let me go on. Now, as I said earlier, we are following a convention where the alpha and beta correspond to an electron with spin in the plus z direction to be plus h bar by 2 or minus z direction as h bar by 2 as beta. But you could have looked at the amplitudes along any other direction. So let me tell you how that goes. Because the reason for doing this is that this introduces you to the notion of a unitary transformation. And unitary transformations play a very important role in quantum mechanics. And we'll see unitary transformations or unitary matrices in the quantum games talk also. Okay, so if you're given this wave function alpha beta, telling you the spin states in the z direction, then the amplitudes to find the electron with the component of its spin along the x direction being equal to plus h bar by 2 or minus h bar by 2 will be given by the upper and lower components of the column that you get by acting on alpha beta with the unitary matrix. The unitary matrix you need is 1 by root 2, 1, 1, 1 minus 1. So if you carry out this multiplication of this matrix acting on this column, you get 1 by root 2 alpha plus beta and alpha minus beta. So the amplitude to find the electron with spin plus h bar by 2 in the x direction is 1 by root 2 alpha plus beta, and minus h bar by 2 in the x direction is 1 by root 2 alpha minus beta. Okay, so use this unitary matrix which transforms you from the z basis of the spin to the x basis of the spin. Where does this unitary matrix come from? So the quantum mechanical description of a spin half electron requires us to define three 2 by 2 Hermitian matrices called the Pauli matrices. Okay, so I have to go into a little bit of maths at this stage, unavoidably. So here are the three Pauli matrices. They're named named that way because the importance of these for describing spin half particles was first pointed out by famous physicist Pauli. So sigma x is 0, 1, 1, 0, sigma y is 0, minus I 0, sigma z is 1, 0, 0, minus 1. You can notice that they're all Hermitian. Their squares are equal to the identity, and they have some other properties which I don't need right now. In terms of these Pauli matrices, the spin operators for a spin half electron are given by the following. So S as a spin operator is h bar by 2 times the Pauli operators. So S is a vector, it has components. So if what this single equation S vector equal to h bar by 2 Pauli vector means is that it tells you the three different relations for the three components of S. So Sx is h bar by 2 sigma x, Sy is h bar by 2 sigma y, Sz is h bar by 2 sigma z. So notice that Sz acting on 1, 0 is h bar by 2, 1, 0, and acting on 0, 1 is minus h bar by 2, 0, 1. And that is why 1, 0 and 0, 1 are called the wave functions for an electron with the z component of a spin being equal to plus h bar by 2 and minus h bar by 2. Okay, so similarly, Sx is h bar by 2 times the Pauli matrix sigma x. So it has this form. Now you can find the eigenvalues and eigenvectors of this. You find that the eigenvector 1 by root 2, 1, 1 has eigenvalue plus h bar by 2. And 1 by root 2, 1 minus 1 has eigenvalue minus h bar by 2. And therefore, these two eigenvectors that you see are the wave function of an electron with the x component of spin being equal to plus h bar by 2 and minus h bar by 2, respectively. And now if you go back, you will see that these wave functions are exactly the columns of the unitary matrix, which transforms from the spin z basis to the spin x basis. Right? So remember these forms 1 by root 2, 1, 1 and 1 by root 2, 1 minus 1. So if I just go back for a second to what we had for you earlier, you can see its columns are exactly those two eigenvectors. So I hope this gives you a general idea of how to construct the unitary matrix, which will transform from any basis to any other basis. Let me also tell you what this electron spin pointing in a general direction looks like. So in the z direction, it looks like 1, 0 and 0, 1. But let's look at a general direction. So a general direction, which I'll call n hat in 3 dimensions, is parameterized by two polar coordinates, theta and phi. So the three Cartesian coordinates of a unit vector n, which are nx, ny, and z, are given in terms of theta and phi as sine theta cos phi, sine theta sine phi, and cos theta. We can then define this quantity, which is the dot product, scalar product of n and s. So n dot s is nx sx plus ny sy plus nz sz. And now the wave function of an electron whose spin component in the direction n is equal to plus h bar by 2 is given by this eigenvalue equation. N dot s psi is h bar by 2 psi. So you just have to solve this eigenvalue equation and find the eigenvector psi. And you find that it's given in terms of the polar coordinates theta and phi as follows. That psi is the upper component is cos theta by 2 and the lower component is sine theta by 2 times e to the I phi. So this tells you that the probability that this state has a spin component in the z direction equal to plus h bar by 2. That's just the upper component mod square. So that's cos square theta by 2. And the probability of this state having spin in the z direction to be minus h bar by 2 is sine square theta by 2. Okay, so unitary transformations play a very useful role in quantum mechanics. Many transformations like the change of spin basis that I just told you about, or rotating the coordinate of a axis of a general system in 3 dimensions, or even evolving a wave function in time, can all be described by unitary operators acting on the wave functions of the system. Unitary transformations preserve the total probability. So that means if psi is a wave function which has probability 1, then u psi will also have probability 1 if we use a unitary operator. Another nice thing about unitary operators is that when they act on operators, they don't change their eigenvalues. So if H is the Hamiltonian of a system and its eigenvalues are the possible energies, then the unitary transformation gives a new Hamiltonian which is UHU inverse. And this is the same eigenvalues and therefore the same energies as H. So notice, by the way, that unitary transformations act differently on wave functions and on operators. So on a wave function psi, u as just acts as u psi, okay, just from the left. Whereas if you have an operator h, then it acts as u h u inverse. So u from the left and u inverse from the right. Okay, so are there any questions so far? Okay, now turns out that these two component wave functions are also often referred to as qubits, which is short for quantum bit. So this is used to distinguish it from a classical bit. So a classical bit also has two possible values, 1 and 0. But qubit is a quantum mechanical object. It's a two-state quantum mechanical system. And we define the basis states as 1, 0, and 0, 1, as we have already seen. What is special about a qubit, which distinguishes it from a classical bit, is that you can superpose the two states and you can write down an arbitrary superposition alpha beta. Whereas you take a classical bit, it can either have value 0 or it can have 1. It can't have anything else, right? You can't have a classical bit taking the values 1 by root 2, 1, 1. Okay, so that way classical bits are much more restricted. You can only have exactly two possible values, whereas qubit is much more general because these alphas and betas are complex numbers. So there's a huge degree of freedom that you can have for quantum bit with two states. So examples of qubits. So now I'm talking about two-state quantum mechanical systems in general, but we have already seen some examples of this. So a spin half object like an electron, where the two basis states correspond to the object having components of a spin in some direction to be plus minus h bar by 2. That's an example of a qubit. And another example of a qubit is a photon, which also I told you can have two possible spin states or polarizations. And there are actually many other examples of qubits in nature, but let me just mention these two right here. Okay. So now let's put two qubits together. So we'll consider a system which has two qubits. So you can consider a system with two electrons, for example. Or you can have a system with an electron and a proton. Each of them is a spin half object. So the wave function of a system with two qubits is given by a direct product of the states of the two separate qubits. So let's work in the spin z basis as usual. And we'll simplify the notation a little bit so that it makes it easier to write down the states. So the notation I'm going to follow from now on is 1, 0 will be called spin up and 0, 1 will be called spin down. So up arrow and down arrow. Okay, so this is to emphasize these two states have components of the spin in the z direction being up and down. Now, these are the states of a single qubit. So the most general wave function of two qubits will be an arbitrary linear superposition of four possible states. The four possible states are up, 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 down, down, up, and down, down, right? So if I take one of them, let's say up, down, the second state. This is a state in which the first qubit is in spin up state and the second qubit is in spin down state. Now, since there are two qubits, there are two sets of spin operators, S1 and S2. They act only on the states of the first and second qubit, respectively. So S1, or if you take any component of S1, like S1Z, it will only act on the first qubit. And S2Z will only act on the second qubit. Okay, so the maths is actually very simple when you go from 1 qubit to 2 qubits. Okay, now it turns out there's a particularly interesting state of 2 qubits, and this is called S for singlet, which I'll tell you why it's called a singlet. This state is the following superposition. It's the state up down minus the state down up, and you multiply the whole thing by 1 by root 2 for normalization. So there are two states here which you have combined, up down and down up. They have a relative minus sign, and each of them has an amplitude 1 by root 2. So if you look at the total probability, the first state has probability 1 by root 2 squared, which is half. Second one also has half probability. So total probability is 1. Now, the reason this is called a spin singlet state is that if you take all the components of the total spin operator S1 plus S2, I have a few typos here. So I just mean total spin, which is S1 plus S2. You can show that this will give you 0 when they act on the state. And this is true for every component. You can take S1Z plus S2Z or S1X plus S2X. All of them will give you 0 acting on the state. So this state has total spin 0. Okay, and in fact, it's the unique state of 2 qubits which have this property of the total spin being 0. Now, I started by saying 2 qubits can have 4 possible states, and here I've only shown you one possible state, S. So there are 3 other possible states. These have total spin 1. So they're called spin triplet states because there are 3 of them. And their wave functions are given as follows. So I've used the notation T1. This is the state up, up. Then there's T0, which is 1 by root 2 up, down plus down, up. This is different from the singlet because even though it has the same 2 states, the singlet has them with a minus sign relatively. T0 has the 2 states with a relative plus sign. And the third state is T minus 1, which is, okay, I'm very sorry for this typo. T minus 1 has both spins pointing down. Okay. Okay, now I come to the concept of entanglement. Now, this is a really quantum property. So let me go over this carefully. So the spin singlet state shown here again is an example of what is called an entangled state. What does this mean? So suppose that there are two observers A and B, and they can only make measurements on the first spin and the second spin. Not just that, let's say A can only measure the Z component of the first spin, so S1Z, and B can only measure the Z component of the second spin, so I'll call it S2Z. Now, suppose there's a third person, like a referee. So the third person just tells A and B that there's a spin singlet state, but you only have access, A only has access to the qubit 1 and B only has access to qubit 2. Now, if they only know this information that the joint state is a spin singlet, then they would not be able to say what the spin state of their own qubit is, right? Because there's a probability of half that will be up down and probability of half that is down up. So that's the best that these two observers would be able to say, that each of them, they'll say that their own qubit has a probability of half being spin up and half being spin down. And similarly for observer B. However, suppose that observer A makes a measurement of S1Z and finds that it's an up state. Now, if you go back to the spin singlet state S, and you see that it's a superposition of 2 states, the one which says the first qubit is an up state immediately means that the second qubit is in a down state, right? So observer A finding their spin to be up immediately tells observer A that the other person, B, will find their qubit to be in a down state. I'm making these typos here. Sorry about this. So if A finds spin to be up, A will know without communicating with B that B's qubit will be in a down state. So this situation is the following, that initially the observers don't know the states of their qubits, but as soon as one of them makes a measurement and finds the state of their qubit, they instantaneously know the state of the other qubit. Now, this holds even if the two qubits and the respective observers are very far apart and cannot communicate with each other, right? So this looks really strange that you make a measurement at your location, and then even if the other qubit is a light year away, you immediately know that if you have found your qubit to be spin up, the other qubit must be spin down. So this strange feature of a quantum system consisting of more than one particle is called entanglement. And this has absolutely no classical counterpart at all. So, everything I've said so far before I came to entanglement sometimes has classical counterparts. Like if you take a single quantum mechanical particle with a continuous set of states like position, it has wave functions which are mathematically very similar to waves in classical mechanics. Of course, the interpretation is different. That in quantum mechanics, the wave function squared is the probability. But if mathematically, at least, we have seen wave functions in classical theories, and you see wave functions in quantum mechanics of particles with continuous states. Okay, so wave functions have classical analogs, but entanglement never has any classical analogs. It's a purely quantum mechanical feature of a system with more than one particle. So it is really something very surprising for a quantum mechanical system. Now, I gave an example of an entangled state, which was a spin singlet state. So just to give you an example of a qubit state which is not entangled, let's consider one of the spin triplet states, T1, which is both spins up. Okay, so in this case, suppose again this third person, the referee tells these observers A and B that this is the joint state of the two qubits, up, up. Then immediately these observers would know, without making any measurements, that the state of the qubit of the other observer is immediately known. So observer A will know observer B's qubit is up, observer B would know observer A's qubit is up, even before they make any measurement of their own qubit. So this is an example of an unentangled state. And it's called a product state. The reason it's called a product state is that you can see that this state, up, up, is a direct product of the states of two qubits separately. Up times up. So this is a classical kind of state. This is, let me go back a bit. This is very different from the singlet state where it's not a product of the state of one qubit multiplied by state of the other qubit. It's more complicated than that. It has a superposition. Okay, so for these two qubits, the spin singlet and this T1, it's kind of clear that one is entangled, the other one is not entangled. But suppose somebody gives you a complicated and arbitrary state of two objects, is there a way of quantifying what is the amount of entanglement that there is? And the answer is yes. So now I'll tell you about a quantitative measure of the degree of entanglement. So this is called entanglement entropy. And it goes like this. So this is going to be a little bit mathematical. So if you take a general two qubit state, then it's a superposition of four possible states, as I said, up, 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 down, down, up, and down, down. These four states can come with some coefficients, which I'll call capital C. So it has two indices, C up, C up, down, C down, C down, down. These are complex numbers. And so Cjk is a complex number which tells you the amplitude of the spin state of the state being J for qubit 1 and K for qubit 2. So J and K can be up or down. So the next thing you do given this general two qubit state is that you define a reduced density matrix of qubit 1. So the way this is done is that you sum over the possible states of qubit 2 so that you're only left with qubit 1. So you have this complex coefficient Cjk. So you define the sum over K, C star Jk, C J prime K. So notice that you're summing over K, which is the state of the second qubit. And the free variables that are left are J and J prime. So this defines the reduced density matrix called rho. It's a 2 by 2 matrix with indices J and J prime, which are the possible states of the first qubit. Now you can show that rho is a Hermitian matrix. Of course, that means its eigenvalues are real, but you can show more than that. You can show that the eigenvalues of rho must lie in the range 0 to 1, and the sum of its eigenvalues is equal to 1. Okay, so these are all the properties of a reduced density matrix. This holds in general, even if it's a more complicated system and it's not a 2 by 2 matrix, these three properties of rho will still hold. Now, in our case, rho is a 2 by 2 matrix, so it has two eigenvalues. Let me call them lambda 1 and lambda 2. Then the entanglement entropy is defined as follows. S is minus lambda 1 log lambda 1 minus lambda 2 log lambda 2. And the base of the logarithm is often taken to be 2 in the quantum information community. So the base of the logarithm, you sometimes take to be 10, sometimes you take it to be e, but in quantum information papers is often taken to be 2. So this is the definition of the entanglement entropy. You have the minus signs. That's important because because the lambdas lie between 0 and 1, their logs are all negative. So you need this minus sign to make the entanglement entropy positive. Now, if you go back to an unentangled state like the spin triplet up, you find that the entanglement entropy is 0. Whereas if you take the entangled state like the spin triplet, you find that S is positive, strictly positive. Uh, for example, for the spin singlet state that I've been talking about, you find that S is equal to 1. And it turns out, in fact, that if you take a 2-qubit state, the largest possible value of the entanglement entropy that you can have is 1. So in that sense, the spin singlet state is maximally entangled. So if you take a 2-qubit state, the values of entanglement entropy can be anything from 0 to 1, and 1 is the maximum possible value. By the way, I should tell you that the reason the word entropy is used here is deliberate. Okay, it turns out that in a very deep sense, the entropy that you're used to in statistical mechanics or thermodynamics, it's believed now that the statistical mechanics entropy is actually at a microscopic level due to some kind of an entanglement entropy. It's the entanglement entropy between a system that you're looking at, the reduced density matrix of the system you're looking at, when you sum over all the states of its environment, which can be a thermal bath. Okay, so this is the reason that the word entropy is used here. So at a deep level, entanglement entropy and thermodynamic entropy are the same thing. Okay, any questions so far? Okay, so let me move on to the last part, which is the idea of hidden variable theories. So this is another strange feature of quantum mechanics. And this is motivated by the idea of entangled states. That's why I'm talking about it here. So let's take the singlet state again. And we know that before we make any measurements, neither observer A or B knows with certainty what the state of their own qubit is. Now, there's a big debate, of how much of quantum mechanics can actually be simulated by some kind of a classical theory. Because, quantum mechanics has a lot of strange properties. It's probabilistic. It has this funny thing that you make a measurement of one thing here, then you immediately know what the value of the other thing very far away is. It has all these peculiar things. So this disturbed many people like Einstein, Podolsky, Rosen, and there are various other people. And so people started searching for, kind of classical theories, which are where the classical nature is hidden, but they're really classical, which can imitate the results of what you get in a quantum measurement. Okay, so is it possible that there can be some kind of hidden variable which we don't really know, but it's there, which is classical, which can lead to results similar to what observers A and B would find by making measurements on this above state? Okay, so an example of hidden variable would be, suppose there's a third person who these observers A and B cannot see. This third person decides randomly to either give a spin up to A and a spin down to B with probability half, or the other way, spin down to A and spin up to B with probability half. So this hidden person, can be just tossing a coin, and depending on whether you get head or tail, this person decides on one of these two things. Now, of course, again, this looks very similar to the spin singlet state in the sense that if observer A would find half the time that their spin is up and half the time their spin is down. But notice that if you have this hidden person, who is giving out spins in this way, in any case, the state of the two qubits would be a product state. It will be either up times down or down times up. So it will not be the spin singlet state. So there's this person, John Bell, who showed that hidden variable theories like this, which are really classical, would give results which are different from what quantum mechanics predicts. So let's consider again a 2-qubit state. And suppose that each of the two observers A and B can make one of two possible measurements. So we'll call this measurement small a1 and a2 for observer A and small b1 and b2 for observer B. Okay, so I'll specify in the next slide an example of what small a1, a2, small b1, b2 is. But right now I'm just saying there are two possible measurements for A and two possible measurements for B. So in all, there are four possible joint measurements possible, right? So observer A can make measurement A1, B can make B1, and so on. So A1, B1, A1, B2, A2, B1, A2, B2. Now, let's say this is done many, many times again. And so we can talk about the expected values for the four possibilities. So let's call the expected value of over what would happen if observer A keeps making measurement A1 and observer B keeps making measurement B1. So E A1 B1, and in the notation that I've used before, let me call it psi A1 B1 psi. Similarly, for the other three kinds of measurements, A1, E A1 B2, E A2 B1, and E A2 B2. Okay, now comes the very important observation that if you really had a hidden variable theory, which is a kind of classical theory, that would predict that E A1 B1 is E A1 times E B1. This is because, as I said, hidden variable theory would mean that A1, the state of the two qubits is a product of A1, of what you'd get from A1 and what you'd get from B1. So a joint measurement A1, B1 would just give you the same result as a measurement of A1 alone times a measurement of B1 alone. Okay. So this would be the classical result. E A1 B1 is equal to E A1 times E B1. I hope that's clear. Okay. So now suppose that each of these four quantities A1, A2, B1, B2 can only take values in the range -1 to 1. So I've not yet specified what the measurements are that I'm talking about. I'll come to that later. So if the measurements of each of these takes values in the range -1 to 1, the expected values of these must also take values only in the range -1 to 1, right? Because if you take the average of a very large number of numbers, each of which is between -1 and 1, the average also has to be between -1 and 1. So using this property and the property in the previous slide that EA1 B1 is a product of EA1 and EB1, we can show that if you take this particular quantity, okay, shown here, so EA1 B1 plus EA1 B2 plus EA2 B1 minus EA2 B2. This minus sign on the fourth term is very important. So first of all, you can write it in this way, in the second line, EA1 times the sum over EB1 plus EB2 plus EA2 times the difference of EB1 minus EB2. And if you think about this a little bit, these are all just ordinary numbers. There's nothing quantum mechanics here. You can show that this total quantity has to be less than 2 in magnitude. So it can only lie between -2 and +2. Okay, so this is called the Bell inequality. That this particular combination of these four terms, if you had hidden variable theories being correct, these four quantities, the sum of these four quantities as shown has to be between -2 and +2. So if you did some experiments on a system, quantum mechanical system, and you got a value which is more than +2 or less than -2, it will violate this inequality, and it would mean that hidden variable theories are not consistent with quantum mechanical theories. So that's the idea. So Bell came up with this a very clear way of distinguishing between the results of hidden variable theories and classical and quantum mechanical theories. Okay, so now let me specify what are the properties A1, B1, etc. that I'm talking about. So let's say that A1 is A1 dot sigma A. So what I mean by this is the observer A measures the dot product of some vector A1, which I'll specify, dot the Pauli matrices sigma A. So we have already seen this kind of dot product before, right? So this is A1x times sigma AX plus A1y sigma AY plus A1z sigma Z. Similarly, A2 is A2 dot sigma A, B1 is B1 dot sigma B, B2 is B2 dot sigma B. So this A1, A2, B1, B2, they are all unit vectors pointing in some directions, which I'll specify in a little while. Okay, so these are the four measurements that I'm talking about. 2 for A1 for the observer A and 2 for observer B. Now you can do a small calculation. I've given you all the information. I've told you what the spin singlet state looks like, right? It's 1 by root 2 up down minus down up. I've also told you what A1 is. It's A1 vector dot sigma A, and B vector B1 Bj is Bj vector dot sigma B. So you can calculate this expectation value, EAI Bj. So Ij can take values 1 or 2. So this expectation value in the spin singlet state psi turns out to be minus AI dot Bj. So this is actually a simple calculation one can do. Okay, so it's just a calculation involving multiplying rho times a main, in which direction A1, A2, B1, B2 point. If you just take A1 dot sigma and take the exponent value of that, that's 0. Okay. Okay, so it's clear from this that EA1 Bj is not the same as the product of EA1 and EBJ and EPJ. So it already tells you that hidden variable theories give you a result which is quite different from what you get in quantum mechanics for a spin singlet state. Okay, so once you know this EA1 Bj is this minus AI dot Bj, the dot product, then this quantity that I just told you about, you can write it as minus A1 dot B1 plus B2 minus A2 dot B1 minus B2. And one can show that given, depending on the choices of these 4 unit vectors, the magnitude of this quantity can exceed 2. So which clearly violates the Bell inequality. So I'll tell you what the choice of A1, A2, B1 and B2 are. Okay, in the next slide. But so let me say at this point that this is a very important concept in quantum mechanics, the Bell inequality. So people have tried to verify or falsify it over decades, many decades. And there have been numerous experiments over the years using photons, using electrons, many kinds of two-state systems, and all of them show that quantum mechanics is not compatible with hidden variable theories. The results you get are consistent with quantum mechanics, but not with hidden variable theories. So now let me give an example of these 4 vectors, a particular choice of these 4 vectors, A1, B1, A2, B2, for which this quantity exceeds 2. So here's a particular choice. You choose these 4 vectors to lie in a plane, let's say the xy plane, and they're rotated successively by 45 degrees. So A1 is 1, 0, 0, so it points in the x direction. B1 is 1 by root 2, 1 by root 2, 0, so it points at 45 degrees to the xy axis. A2 is 0, 1, 0, points in the y direction, and B2 is minus 1 by root 2, 1 by root 2, 0. Then for this particular choice, you can calculate the quantity given at the top of this slide, and you find it's minus 2 root 2. So its magnitude is clearly larger than root 2, clearly larger than 2, which is the Bell's bound. Okay, so the 2 things here. One is that we have given an example of 4 vectors for which you get a value which is outside the Bell inequality, more than 2 in magnitude. It turns out that 2 root 2 is the upper bound of the magnitude, and this was proved later by a person named Cyrilson. Okay, so there are actually 2 different inequalities. One is the Bell's inequality. So quantum mechanics violates Bell equality and gives you something which is more than 2 in magnitude. But Cyrilson is a different bound which tells you it can be more than 2 in magnitude, but no matter what, it cannot be more than 2 root 2. Okay, so let me summarize. So I've told you what wave function is in quantum mechanics, what is its interpretation. Basically, it gives you the probability when you take the mod squared. I've told you about the spin half nature of the electron, and this leads to the idea of a qubit, which is a general term used for 2-state systems. I've talked about two qubit wave functions and the idea of entanglement. And finally, I've told you about the Bell inequality, which can distinguish classical hidden variable kind of theories and quantum mechanical theories. So I'll stop there. Okay, the last slide is on a couple of references. Now, all that I've told you is given in many books on quantum mechanics, but there are 2 which I find particularly easy to read. There's a comparatively recent book by Krishnendu Sengupta and Palash Pal called Introduction to Quantum Mechanics. And then there's a book by Franz Schwabel called Quantum Mechanics. So you can look at these, but as I said, everything I've told you today is there in many books in quantum mechanics. Okay, so let me stop there. Let's see if there are any questions.
Thank you, Professor Shane. That's a wonderful lecture. Please, let's thank. Any questions? Yeah, you can just speak loudly and it will catch.
Is there any way to figure out if a state is entangled just by looking at the notation that you were using?
Yeah.
Mixed,
So,
mixed state
yeah,
doesn't
this is the way. So you're asking whether there's any way to figure out if a given state of two objects is entangled or not, right?
Right.
Yeah. So this is the way to do it. So first of all, you write. So I'm telling you a state two qubits. So you write it as this linear superposition of all the basis states. So basis states are arbitrary states j of qubit 1 and k of qubit 2 multiplied by some constants c, j, k. Then you define the reduced density matrix. You sum over all the possible states of one of the qubits. So let's say the second qubit. So you're summing over k. So j and j prime are free variables. So you get this reduced density matrix. Rho j, j prime. Right? Then you find the eigenvalues of this reduced density matrix, and then you combine them, define the entanglement entropy. Minus the sum over the eigenvalues lambda j log lambda j. Now, so if the sum turns out to be 0, and that will only happen if each of the lambdas is either 1 or 0. So if this S is 0, then it's not entangled, and if S is not, it's positive, then it's entangled. Now, there is something very interesting about this way of finding entanglement entropy. So I told you that you sum over the states of qubit 2 and you get a reduced density matrix of 1. You could have done it the other way, right? You could have summed over states of qubit 1 and found the reduced density matrix of qubit 2 and find the eigenvalues of that. Find the entanglement entropy. So the amazing thing is that it doesn't matter which way you do it. As long as you have a system consisting of two parts, you can find the reduced density matrix of either part by summing over states of the other part and calculate the reduced density matrix, find the entanglement entropy. You will get the same value, regardless of which part you do the calculations on.
Generally,
So anyway, I hope this answers your question of how you find the entanglement entropy.
but generally, mixed state doesn't necessarily mean entangled, right?
Mixed, that's true. Mixed state doesn't mean entangled. So, for example, you could also have a mixed state where rho, let's say, is so suppose it's a state which is up with probability half, or down with probability half. So that's an example of mixed state. So this is not coming from a single state. This is just two different states, up and down, which have probability half each. But there also, you can call this a density matrix and calculate the entanglement entropy. Okay. So let me say that entanglement entropy can be calculated either for a pure state of two objects, or it can be calculated for a mixed state. What I've told you is how to calculate the entanglement entropy of a pure state. Okay. So for pure state, this is the way you do it. You find the reduced density matrix. If you have a mixed state, then the way to describe mixed state is already using a reduced density matrix. So you don't have to do the first part of the calculation. You already have a reduced density matrix, rho, and then you find the eigenvalues and calculate the entropy.
Yeah, Mahesh. Yeah, you can speak loudly.
Okay, so I'm just trying to interpret this entanglement entropy through a slightly static perspective. So,
sorry, I can't hear you very well. Can you just speak a little more loudly, please?
So I'm just trying to interpret this entanglement entropy through a static perspective. So if I start with an entangled state as my initial state, and I describe a certain dynamics, will this entanglement entropy always increase with the dynamics as the entropy increases through any thermodynamic process, or?
Yeah, it would. Okay, but first of all, you have to learn how to calculate the entanglement entropy between two parts of a system. So the way it goes is like that. So you consider the entire universe, let's say. And then it has two parts, which is your lab, for example. That's one part. And then the rest of the universe, which is the environment. So let's say the entire universe is in a pure state. It's defined, you're in one particular eigenstate of the Hamiltonian of the entire universe. And you take one particular eigenstate of that. Then you break it up in this form given at the top of this slide. You write this pure state as a sum over superpositions of states of your lab times the rest of the universe and calculate the reduced density matrix. And from that you find the entanglement entropy. So the idea is that in all the cases, I don't think it's been proved completely generally, but in all the cases known where this calculation can be done, people have shown that this will exactly reproduce what you're familiar with as the thermodynamic entropy of the system that you're interested in your lab. Okay. And then everything that applies to thermodynamics, like the entropy increasing with time, will also apply to entanglement entropy.
Thank you.
So entropy of a black hole can also be understood in this way, it turns out. You can understand the entropy of a black hole as some kind of an entanglement between the interior of the black hole and the rest of the universe.